see the screen now?
Yes. Yes, we can see yours.
Okay, great. So what we can do? Okay, so let me turn off the camera for better audibility.
Yes.
And okay. And then I should maybe use full screen mode. Now it is better?
Yes,
Hello,
it is
Mahesh.
clearly. Yes, it is clearly visible.
So fine, right?
Right.
Okay. Hello, everyone. So today we are going to talk about data-based criteria for controllability of LTI systems. By LTI, I mean linear time invariant, that we will soon go through its definitions and all the things that are related to this talk. So in machine learning, it is like a very fundamental question, and I would say like most of the engineers are hired to ask the good questions, like you have the data, so much data, you have rich data, but what you have to do and for what you are paid is to ask good questions, like what you can infer from the data, and is it important to know that, and why it is important to know that. All these good questions that you can ask and you can find answers. These are the things we do in machine learning. So why I want to ask this question, like I have the data, I want to know the controllability. Why it is important? Of course, controllability is a very important property for any system. And I used to say like controllability as ability to control. That means you have some physical system, engineering system. If you can control it, then it is meaningful. Otherwise, what is the use of the system? Okay, with this, let me just give a simple example. For example, suppose I'm driving a car and I want to achieve certain speed. So what I can do, I can use accelerator as my control variable to reach that certain speed. So here what is the main thing? Accelerator, that is my input, and the speed, that is my output. These are the two variables in which I am interested. What else is being done during this process, I do not care about it. I would supply some control input variable and I would observe or measure my speed. That's what. So these two variables, input variables, output variables, for which a model aim at describing are called manifest variables. The rest variables like inside you might need to know the temperature of your engine, the position of your car. These are not important to us, and those we call as latent variables or intrinsic variables. A special case of these are state variables. That has also some applications that we will see in a minute. So with this, I think I am ready to give you some motivations. So let me set the stage so that we can talk more rigorously. Okay. So what is my setup? As I said, I am considering linear time invariant systems, but in discrete time. That means I would measure the data in time samples, say 1, 2, 3, 4, 5, not continuously. And the second is, I assume that the data that I am measuring is exact. That means it is noise free, because it is a common understanding that when we measure any data, it is corrupted. But this is assumption that we are the data that we measure is exact, noise free, so it gives rise exact model B. So I have the data, I can identify the model B. So this is my setup, that my data WD is generated by some LTI system, and I want this data to be exact so that I can identify the true model B. So the message, as I said, our message for this talk, or the takeaway of this talk, is we want to know whether the system is controllable or not based on this input-output data, these measured data. As I said in the beginning, there could be other data like state data and other latent variables, but that you cannot measure. What you can measure is just input and output. So this problem of knowing whether a system is controllable or not based on this data has really, many importance, because uh, I hope the familiar reader must know that controllability is a basic assumption in designing problems. Like if you want to design a feedback control to achieve something, or for a performance index, controllability or a weaker concept, stabilizability, is a standard assumption that you assume on the system before doing anything on the system. So, and now, like these days are in the recent times when we cannot actually know what the model is, but we could know the data. So based on that data only, we can ensure that yes, the system is controllable. We can go ahead and design these controllers to achieve our specific goals. Okay, so let me just quickly introduce like what is the dynamical systems, what is LTI systems in my way, so that we actually communicate. Okay, so even before I learned this subject, when someone say system or model or a dynamical system, even I used to perceive as equations, like there are certain system of equations that is my system, and it is dynamical in the sense that it evolves over time. But you see this definition, a dynamical system is just a triple TWB, very natural definition. Like I just want to have three tuples TWB, and what are those? T is my time axis, W is my signal space where my data lies, and B is the behavior, that is set of all functions from T to RQ, T to W. WT, usually it is a standard mathematical notation that consists of all functions from T to W. So you see, this is so natural that I just want to know only my spaces, the time space, the signal space, and the set of all trajectories from T to RQ. That we call as behavior, because this is the most important thing that defines the system and that we are interested in. As I said, we are interested in applying some acceleration to achieve some speed. The rest I don't care. And this is the only thing that I want to, and this is the only thing that a model should be representing for a user. So my main focus would be behavior B. And once I have the behavior, that means B, so I inherently know my time T and the signal space RQ. So I could interchangeably use the terms dynamical system or behavior B. For this specific talk, I presume the time is subset are equal to the set of natural numbers. That means we are discrete time setting. Having discussed the dynamical system, let us now move towards LTI systems. So before that, we need some more concepts. So the first concept is a shift operator. That means this acts on WT and maps to WT. So what it does, if you apply some time T, it sends you to time T plus 1. So it is a kind of backward shift operator. And then what do I mean LTI system? Okay, well, so first of all, as I said, there are three components, TWB. So we say it is LTI if W is a vector space. That means you could have superposition principle. If you add or multiply by a constant, you're still in the set. And time invariant means if you apply shift operator to each and every trajectory of the behavior, you will again live inside the behavior B. And this last is very important, that even if you do it, say, infinitely many times, it still lies in the behavior B. So it is point-wise convergence. So if you have W1, W2 up to W, so on, if you apply shift operator, you will again, all those new trajectories will be inside the B. So this is also closed in the topology of point-wise convergence. And suppose you collect all such systems, that we denote as LQ. So my LQ is set of all LTI systems. Okay. So it is quite natural, but still let me just say that once you have the behavior, you can always write this as many ways to write, like state space systems, kernel representation. So for any behavior B, for any LTI system B, we can always express it as R of sigma, sigma is my shift operator, times W equal to 0, and we call it as kernel representation of B. So just a quick example. So suppose you have a dynamics that evolves like W1 of, so it has two components, W1, W2, and W1 of T plus 1 plus W2 of T equal to 0. So you can write as sigma 1 W1 W2 equal to 0 as R of sigma W equal to 0. That is, it has a kernel representation. So, and you can see that if you have one kernel representation, you can multiply by a unimodular matrix, here just a constant, to get infinitely many representations. So for a given behavior B or model, we can have infinitely many representations, and this is the kernel representation that I just showed you. There could be many representations. I may talk in a minute. Okay, so this is the main guy who laid the foundations of these behaviors, Professor John C. Williams. He is a Belgian mathematician, and he actually invented this concept in 1980s. And I would just, as I already introduced you, what is this? I would just quickly go through the key features. Like there are models, there are LTI systems. Those are known before he invented this. So once you propose a new theory, you have to be like make it happening. And to make it happening, you have to have some relation, some connection, what you know beforehand. And for that, I would just quickly recall the key features. Like once I have this theory behaviors, what is the key features? Why I am interested in this? So the first, as I said, the dynamical systems are not the equations. They are actually the trajectories and valid trajectories. That means they satisfy the model that we call the behavior. And this notion of behavior, as you see, it is representation free. I mean, I do not need any equations to understand what is my dynamical system. Before that, it was mainly state space models. That the first thinking is that you write this equation and then what it pops up as UV is your behavior. But no, this is not the good way of thinking. The thinking should be other way. You have the trajectory and let the models describe it. Okay. Apart from that, there are other concepts before it that was existing is transfer function approach. In that, you have to have the partition of input variables and output variables. But in this behavioral approach, even we don't need to have a priori partition of input output variables. So in a sense, it unifies all the existing previous approaches. As I said, transfer function approach, where you have partition of input output variables, and transfer function is a map that maps each input to output. And the state space model, as you can see here, x of t plus 1 equal to axt plus but and y of t equal to cxt plus dut. This is a representation of a model that is actually coined by Rudy Kalman. Rudy Kalman is a Hungarian-American engineer come mathematician who actually coined this sort of equations, and it has, I mean, I must say it has tremendous applications, and one of the most important application is the Kalman filter, and it is highly used and it works very well in this representation. So it has also applications, or you can say it has it has a kind of very good numerical techniques that has been developed over time that works pretty well for these systems. So this system is a nice one, but as I said, this system has the thing is that if you start with a model, you think of only as a trajectory input output, not as equation, and let the equations come later. So state space systems could be a better way to represent those model. Okay. And the nice idea that comes from this behavioral approach was the most powerful unfalsified model. That means I would like go through it quickly, but let me just say a few words about this. That for a given time series or the data, I could find the exact model that describes this time series, and it is most powerful in the sense that it is the least complex model that describes this time series. Okay, enough of the behavioral system theory. Now we are back to the maybe 100 or more than that years back. And this gentleman, Hermann Hankel, thought of a matrix, simple matrix. You see, he thought of a matrix HL of WD. What he says is that you can see that all the diagonal elements are equal. So originally it was defined for square matrices. So you may mean all the diagonal elements are equal, and if the matrix is square, so it is inherently a symmetric matrix. So you can do a lot of things once you have a symmetric matrix. But here we extended this Hankel matrix to cope up with general sizes like general dimensions. It could be rectangular as well. So for a given time series WD, we define a Hankel matrix in this way, that it starts from WD of 1 and up to L block rows, and then you can easily see that if you intend to end up at WD of T, it has T minus L plus 1 columns. This Hankel matrix has several applications, and recently, like all the low rank models would actually come into this structure that is Hankel structure. And once you have this structure, life is easier. You can do a lot of computations. And this matrix is very much used in machine learning techniques. And this is the matrix that I also used when I would discuss my main results about data-based controllability. So this is very important matrix to note. And you see, the idea is very simple. You just need to put elements equal on the each diagonals, and this, I mean, lead to a kind of new structure in a matrix that is being used recently in a lot of applications. Okay, a little bit of nomenclature that I would use. So as I said, I will start with some data. So a time series WD, that is WD belongs to RQT. That means each W is a member of RQ, and it has T components, that is WD of 1, WD of 2, and so on up to WD of T. So we call this time series as persistently exciting of order L if the Hankel matrix HL of WD that I just defined is full row rank. So once I have a time series, I can check whether it is persistently exciting or not by checking the rank of this matrix, Hankel matrix. This is the one thing. Other thing, as I said, most powerful unfalsified model. This is defined by Jan C. Willems, and the idea is simple and is like Karl Popper was a philosopher come mathematician who used to say that the more a model forbids, the better it is. So utilizing his idea, he said the model should define the data, but it should be least complex. That means it is forbidding all other things. It should be least complex. So that he called as most powerful unfalsified model. And the complexity as is defined is the ordered pair, number of inputs, comma model order. Number of inputs, you know, if you have a model, you have certain free variables that you call as inputs, and model order is that, as I said, I have a model, I have a trajectory, I can model it as a state space form, and once I model it in a state space form, and I can transform it to minimal state space form. That means the number of state variables required to describe this model is the least among any others. Those, as the state cardinality, we say model order. And this he defined in a lexicographic manner. These are reasons to do that, because it actually turns out that it depends more on the number of inputs than the model order. So if a model has more number of inputs, I mean, you have more freedom, more free variables, so it would be always more complex than the model with less number of inputs, irrespective of the model order. And so, as I said, this my time is n, set of natural numbers, discrete time. But if I actually want to do experiments, if I actually want to do some real life thing, I cannot have measurements or observations for infinite time. I must cut it down. So in this way, what we thought of like restriction of B to the interval 1 to L, and that we call as B restricted to L. And that essentially says that we are looking for finite length trajectories. That is W1, W2, W3 up to WL. Okay, so now back to the original concept of controllability as we started off. So the moment we have agreed that we will look model as a set of trajectories, so the controllability is a natural way that if we can join, say I have two trajectories, WP and WF, if I can find a new trajectory that could join this, we say it is controllable. And if I cannot do this, we say it is uncontrollable. In a more mathematical way, like if you have two trajectories WP, WF in V, and there is another trajectory WC, such that you concatenate like WP, say up to T1, and then from T1 to say T2, you have WC, and then from T2 onwards, you have WF. We call it a full trajectory W. This goes inside B, then we say this is system is controllable. And as I already pointed out, that for each model, you can always write it in a kernel representation, R of sigma W equal to 0. So the algebraic way of testing this, you just need to test the rank of R of lambda for all lambda, and if it turns out to be the same for all lambda in C, set of complex numbers, then we say the system is controllable. Perfect. Now, so with that, I think I have, we all are ready to talk about the data-based necessary and sufficient condition for controllability. So, as I said, we have a trajectory WD, that is WD of 1, 2, 3 up to T. Now, you take the snapshots and collect it in this way, that WD of minus contains 1, 2, 3, and so on up to T minus 1, and WD of plus contains 1 time instance ahead, WD of 2, 3 up to T. Now, this is just to make the things compatible. once we can, like, I can observe this data, I can make this thing happen. And now I am going to state the main theorem of this talk, the main result about controllability, that is data based. Some people also call data driven or model free. So these are the synonyms for this kind of work. So here we are saying as data based. Okay. So let WD in be restricted to T. That means I have a trajectory up to length T, and I assume that this trajectory is generated by LTI system. That means B is in my LQ, set of all LTI systems. Then I choose some L greater than or equal to N of B. N of B is order of B. As I said, if I have B, I can transform it to a state space system, and the minimal state space system, that state cardinality is called order of B. Then as WD contains inputs and outputs, so I have the input sequence UD such that it is persistently exciting of order N of B plus L plus 1. That means I need to construct a Hankel matrix of order this, and if it is full row rank, then I would say yes, it is persistently exciting of this much order. So once you have this nice data, you can construct HL Hankel matrix with WD plus and Hankel matrix with WD minus, and then HL of WD plus minus lambda times HL of WD minus, and you can compute the rank, right? And if it happens that for all lambda in C, for all lambda in complex numbers C, if this rank coincides with N of B plus M of B, means number of inputs in B, like how many free variables you have in the system, times L, then you would say that the system is controllable. Beautiful. It only depends on the data WD, and also a bit that you know M of B, because once you know the data, you know M of B, and the order is something that is need to be taken care. So if we know these things, we just say that whether this data is generated by a controllable system or not, irrespective of whether we have a representation or not, because before that, like, controllability is always associated with the representation, like Kalman test, Hartus test. They all need the matrix A, B to infer the controllability. But here, once I have the data, based on that only, we can say that the system is controllable or not. And analogously, if this lambda is such that absolute value of lambda is greater than or equal to 1, that is, it lies outside open unit disk or in the complement of open unit disk, and if this equation 1 holds for those lambda, we say that the system is stabilizable. So here, as I said, this is weaker because you see we have put some constant on the lambda, so we don't need to check for all lambda in C, rather just those have absolute value greater than or equal to 1. So if satisfies for those sets of lambda, then we say that the system is stabilizable. So this result based on the data only, and it shows that whether the system is controllable or not, whether it is stabilizable or not. So the moment we have this result, as you see, this HL of WD and HL of WD minus are rectangular matrices in general. So it is hard to find, it is hard to find the way to check this condition. So for that, our next goal is to develop some algorithm so that we can actually make this test in computers to work with and to simulate and to have several applications, so that it's not that just a theoretical result, but we can have ways to test it, and then we can apply it to any kind of LTI system. So before we do that, just quick remarks. As you see this, it's kind of hottest test. Hottest test, as I hope the familiar reader would immediately find this, but for the sake of the people who are not familiar with the literature of control, I would just say that it is here. So you need to find all lambda in C such that the rank of this matrix coincides with n, and it actually turns out that you only need to check the eigenvalues of this matrix A, because those are the only lambda responsible where this matrix is going to be rank deficient. So this test is similar to hottest test, but here in hottest test you need A and B, but it does not need any kind of representation of a model. So we just need the data, that's all. The second is, as I said, it can be verified directly from the input-output data. And why actually we dig into this problem was the motivation of this result, which is a kind of instrumental in the recent development in data-driven control that is called as fundamental lemma. So the fundamental lemma essentially says that if you have a controllable system B and you have a trajectory WD, finite length trajectory restricted to T, such that inputs UD are persistently exciting of order L plus n of B, order of B, that you can check using Hankel matrix test that we just talked about. Then column span of HL of WD. That means you can take linear combinations of columns of this matrix HL of WD, and that would give you full model. So this is very powerful because it implicitly identifies the model that if the system is controllable and the data is such that inputs are persistently exciting of order L plus n of B, then all the trajectories of the model can be written as a linear combination of the columns of the matrix HL of WD. So when I looked at this result, I thought, oh, this UD is PE, persistently exciting. It is easily verifiable from the data. But how would you ensure, just based on the data, that your B or the J is also controllable? For that, you need to identify the model. So it always boils down to identifying the model. So I thought let us have some conditions so that just based on the data only, I can also say that B is controllable. Then it is a very nice result, and then people can easily say that, okay, I have this data, it is coming from a controllable system. Inputs are PE of order this. So I can apply the fundamental lemma to recover all the trajectories, in turn to recover the model, and then they can do whatever they like to do, design controllers or whatever. Okay, so this was the motivation for this work. So this is the crux of the matter. And with that, we started off with that I want to find a test based on data such that the system is controllable. And eventually, fortunately, we got it and we just talked about it. Now, as I promised, we will see how actually we compute or how actually we test that result in computer. So for that, we develop an algorithm. So what we need as input, we need observed time series WD, order of the model, and the number of inputs in B. And we can choose a window length L that is larger or equal to order of B. And what is the output? B is controllable or uncontrollable. So how we can do that? Well, let us start. So if you remember, okay, so just leave it. I will just quickly go through it. So if you remember, I have these two matrices, HL of WD minus and HL of WD plus. So what I did is I first took the SVD of singular value decomposition of this HL of WD minus, and once I have the SVD of this, let's say S00, I can designate R as the rank of this matrix, and then I can apply the same transformation matrix UNV to the other matrix HL of WD plus and break it into the 4 parts corresponding to this. And then you see I have lambda only in this first block matrix, and these are square matrices, so I can always play with generalized eigenvalues, and I have computed these generalized eigenvalues, and these are the only lambda which makes this matrix to drop the rank, and thus we are all set. So we just need to compute the rank of this matrix for all generalized eigenvalues of H11, S. And once it drops, once it achieves the rank n of B plus m of B times L, actually it should be L, capital L. So I just say L plus 1, I just put it. Because I forgot to actually change it. I had some presentations previously where I used to talk about the lag, and that's the different things. So it should be here capital L as we discussed here. So, and if it equals to, because I just need to take L is just anything that is larger than or equal to order of B. So essentially I can choose L plus 1, but it is better to have L just for the unification. So if it coincides with this much, if the rank of H lambda coincides with n of B plus m of B times L, then we say that the system is controllable. Otherwise, we say the system is uncontrollable. Okay, with this, as I said, so the fundamental lemma that is very important in data-driven control theory, and almost all the results uses in one way or the other this lemma to come up with new techniques for control laws. So once I have this test, it is easy to verify both the assumptions of the fundamental lemma, that is whether the system is controllable or not, and the other assumptions that inputs are persistently exciting of order L plus n of B is already seen to be verified by the Hankel matrix. So with this result, we can verify both the assumptions of the fundamental lemma. And the other thing is that, as I said, knowing the order is sometimes a tricky thing, but knowing the upper bound of the order is pretty easier. There are techniques to find, or at least to find, I mean, you can always find the order of the model, but it's easier to find an upper bound of the model. So suppose I have the access to an upper bound of the order. So can I say something about this result? And when we looked into this problem, we found that yes, we can say something. And what we can say is that, as you have seen, that if B is controllable, implies rank of this Hankel matrix, rank of this matrix pencil, HL of WD plus minus lambda times HL of WD minus equal to N of B plus N of B times L. So that is, if controllable, this matrix has fixed rank. So suppose I have access to the upper bound of order, say NU. I can choose NU as L, and I compute the rank for this Hankel matrix, for this matrix pencil. And if it is non-constant, then clearly B is uncontrollable, like P implies Q, minus Q implies minus P. So if we have access only to the upper bound of the order, we can possibly say that the system is uncontrollable. Okay, enough of this. Let us have some like simple things and some examples where we can actually test these results. So the first thing that is easier and easier to see and easier to do was test this result for random systems. So just for the sake of presenting here, I choose a single input, single output system of order 4. So this is a very simple, you have a MATLAB command DRSS. With that, you can generate any system, random system. Just need to give the order, number of inputs and number of outputs. You can find a random system. And then I generate the output using again the MATLAB LSIM command. And I have now the inputs and outputs. And I found that the system is controllable. So it was, oh yes, great. This is very nice because random systems are usually controllable because of the fact that if you go back with the hardest test or with the Kalman test, so it depends on the matrices. And if you choose a random matrix, most likely it is going to be full row rank, or in this case full row rank because you have less number of rows. So if you choose any random matrix, most likely it is not going to be rank deficient. So with that link and also with our results, we can say that, oh yes, the random system of order 4 is controllable. Then we test this I just wanted to see the time, like how I'm doing with the time. So I think I am pretty good. Okay. So the next example that we tested is RLC circuit. And here you see we have a circuit, and as you see, my manifest variables are current and voltage, and this CRC, LRL are the parameters of this circuit. And then these are my model parameters, CRC, LRL, and then manifest variables IV. Then I could write, like using basic Kirchhoff's laws, we can write down the system equations, and then we can eliminate the latent variables. So I can have these behavioral equations. So I have this kernel representation R of S as PSQS. PS is this and QS is this. And we already recognize that this system is uncontrollable if we choose the parameters like this, that is theta1, that is theta3 equal to theta1 times theta2 square, and theta4 equals to theta2. So if we choose, for instance, all equal to 1, essentially this satisfies this assumption of uncontrollability, and we end up with a transfer function like this. So if you see, you can cancel out this as numerator and denominator. So it's just a static unit gain from the input-output thinking. But it actually has second-order dynamics, which a transfer function cannot capture, because the transfer functions can only capture controllable systems. So to see this, what we did, we wrote observable canonical form for this transfer function, which is given by ABCD. These are the matrices that gives me the state space system. And now I have this system, I can easily simulate it, and I can find the trajectories, and I can apply the algorithm 1 to check whether the system is controllable or not. And we found that the system is uncontrollable. That matches our, that matches what we know a priori, that system is uncontrollable for these parameters. So with this, we have also utilized our results to the real world, circuit examples as well as random systems. And we have this result, and we can use to any LTI system as long as we have the data. So in short, and to conclude the talk, what is the message of this talk is that we can actually infer the controllability of a system based on just the data that is generated by the system, and even more by just the input-output data, not the state data. And these are my co-authors, Professor Ivan Markowski and Dr. Ben Grossman. And a few references that I would like to share for, and I find them useful to read. And if you are also looking to have more details about this, you can quickly read them. So all these materials, this is just one theorem, of course. So you can find the more details about this talk and other results in reference 5. And here in reference 4, you can find the fundamental lemma that I talked about, and you will see it has a lot of citations. This is widely used in recent days. And here, actually, this paper number 2 is actually where Professor Williams said the definition of most powerful unfalsified model. And it is a kind of report paper that where he wrote down everything what he have developed until 1989 in the context of behavioral system theory. And this reference 1 is, it's very general matrix computer science books. So if you intend to do some research in matrix theory, I would strongly recommend you to have a look at this book. It is very nice book. And thank you for listening. And if you have any questions, please feel free to ask. Thank you.
Participants, if you have any question, please ask to Dr. Vikas.
You can also leave your questions to the
Comment
chat
box.
box in the right panel. Yeah.
Yes. Okay, so if there is no question, thank you, Dr. Vikas, for such an interesting talk. And we will have our next lecture after half an hour at 4 p.m.
Okay, Mahendra, thank you. Thank you for having me. Bye.
Bye bye, Vikas.